speaker is my dear friend Johan Fougerolle from France. And 5 years ago, well, more than 5 years ago, it was what I call a sad moment for science, when he decided to start his own restaurant. But then, now 5 years later, let's say he has come back to academia, and now we are continuing our research on R-functions. So it's really my pleasure to introduce Johan. So again, you will see many overlap with things which have already been talked about in the symposium. So please, Johan.
All right. Thank you very much, Johan. Before I start, can you all see my screen? No problem. And if I switch tabs, you can see the screen as well?
Yes.
Okay, perfect. So everything's on track. Well, first of all, thank you very much, Johan, for inviting me. This is typically for this kind of days that doing research is cool, because you meet interesting people, bright ideas, you discuss problems. So that's really, really enriching. So thank you for the organization and all the presenters for their presentation. So long time no see. And I have been working on R-functions and supershapes for more than 20 years now. And so this is a very recent progresses that we have done since I came back to academia in last January. So I'm very happy to present them. It's a collaborative work with Aurore and Joachim. Joachim is online, he's following the symposium right now. And you, my friend, Johan. So the question is, can we build our functions using geometry? Let's first start by the context and the motivation of this work. I work in computer vision for robotics, so I'm not a mathematician, and we need robust, compact, and efficient tools for robotic environment and shape understanding. So the general idea is that we might have several types of drones that can be flying drones, that can be mobile robots, that can be underwater robotics. You can think of whatever you want. And those robots or drones are equipped with several types of sensors. So we have various types of cameras. They're equipped with LiDARs, with n-dimensional scanners. And usually we deal with, in a general problem statement, with heterogeneous data, real world, which means it is an uncontrolled environment, and real-time acquisition and data. So our problem is to be sure that the robots correctly understand their environment so that they can efficiently perform the task they've been assigned. So in order to do that, we need some representation of the world, some representation of the objects that the robots might encounter, so that they can track them, recognize them, or take them to move them wherever they want. And usually, especially in the field of robotics, simpler primitives are preferred. So usually planes or hyperplanes, spheres are largely enough. So I'm not going to talk about super shape and super formula today, maybe next year, okay? So basically, as I said, we have robots, we have autonomous or mobile robots, and we first need to localize the robots within their environments. So the most important question that we might need to answer is, can we build distance-like functions to represent the world? So can we equip the robot with some ability to know if he's getting closer to a wall or if he's getting further away? And if the answer is yes, because that's the case, can such functions be efficiently used? How and why? So, most of the traditional approaches in computer vision, generally speaking, they first extract several kinds of descriptors, and then they use them for various tasks, such as clustering, classification, and tracking. So this implies from a very first point of view that you do not represent the world. You first discretize the world into descriptors, and then you use them, which implies that the results depends on the chosen descriptors. How many descriptors? Are those descriptors robust? Are they characteristic enough of the feature that you're seeking within the world? And of course, such approach has several limitations. So before the rise of artificial intelligence, the trick in computer vision and the challenge was to find the best descriptor, the most tailored and accurate descriptors for specific tasks. So which means that at that time, most of the descriptors were mostly application context dependent. And nowadays, with artificial intelligence, or more generally speaking, deep learning, for each problem, we start by training one or several neural networks. We observe how good or poor or bad they perform. We adjust, we tweak them, we change their structure, and we rerun. This approach is tremendously efficient, and it has been used in many, many applications. Can be recognition, medical imaging, autonomous robotics. I mean, we all know these applications. In our case, we don't want to use this amazing amount of computational geometry. We want something simple. We want something to be efficient, and we don't want to have any kind of pre-training or learning process. Okay, so we don't want to model the world using descriptors or using AI. We want to model the world using functions and not only descriptors. So one family of functions that can be used to achieve such tasks is R-functions. So the first question is, why should we use R-functions? First of all, R-functions have been used they've been introduced in the late 60s, and they have been used in very, very numerous fields, including computer graphics, simulation, robotics, geometric modeling, mechanical engineering. And the key idea behind R-functions is that R-functions allow to perform Boolean combinations of objects. As soon as each object is a closed surface implicitly described by a function, then it can be combined in any Boolean manner we want. So it is an extremely powerful tool. And the problem that I'm partly addressing in this presentation is that classical R-functions are binary functions. So as soon as you start creating complex Boolean operations, you create some kind of binary hierarchical tree of combination that can become imbalanced. And by doing that, you completely degrade the behavior of the value of the R-function. So my objective today is to present the methods to build an associative and balanced manner, if possible, to come up with cool and distance-like R-functions. Okay, for those of you who are not familiar with R-functions, what is an R-function? An R-function is simply a function whose sign is solely determined by the sign of its argument. In other words, you can see the resulting sign of the function as a Boolean operation of the sign of its argument. So it means that you can build any Boolean operator and convert its result as a positive or negative value for your resulting functions. So the trick is that the sign of a R function only depends on the sign of its argument, which means R functions, they do not depend on the magnitude of the arguments. And most of the work of Vachev from this observation has been to create and build smooth analytic operators to have the desired differential properties. So if you are not familiar with R functions, here are the three main branches that have been introduced by Vachev in the late 60s, 70s. It's written in Russian, so many of us, me included, don't speak and don't read Russian, but you can find a very comprehensive paper by Vadim Shapiro that has been published in 2007, if I'm correct. So the first family of R functions is called the R alpha function. And you can see it's not a very complicated function. It basically takes the coordinates of a vector x1 and x2, sums up their coordinates, subtracts some kind of square root of the squared sums, and is only controlled by this alpha coefficient, where alpha just needs to be some kind of bounded symmetric function. The simplest application of this function is by setting alpha to 1. And when you do so, then these R alpha functions turns to become the minimum and maximum functions. So fairly simple functions to use and apply. The second and probably the most widely used family branch of R function is the RP function. And it looks mostly similar to the previous function by setting alpha to 0, but the logic and the reasoning that led Radchev to come up with these functions are really different. So this is why Radchev himself insisted on the fact that those functions should be distinguished. What matters here is that we can control the differentiability level by the p parameter in this equation. And once again, nothing's very complicated. You take x1 and x2, you take the p-est norm of x1 and x2, and then add or subtract that. The last one, not that widely used, but it's just, once again, adding a multiple factor in order to control and to improve slightly the differential properties, especially at the origin, by adding the last terms on the right. Not that very important, but those are the three main branches of R functions. Before I go further, I'm going to show you what they look like. So here's the R alpha function for the intersection. What matters here, okay, in blue and dark blue are representing the negative values, and in shades of orange up to yellow, red are represented the positive value. What matters the most is that here I just consider the intersection, which logically corresponds to the conjunction, of values, and we can see that the part of the space here for which the function is positive corresponds exactly to the location in space where both coordinates are positive. So it actually represents the space where x1 and x2 are positive. Okay? The second type of R function is as follows. Once again, we don't change, of course, the sector in which the function is positive, but we do change the way the function evolves over space. And the last function is like that. And if you want a better representation using the height to have a better glimpse on how those functions evolve, we can see here how they behave and how they look like in 3D, okay? So, of course, those parameters, they have their strengths and weaknesses, which I will summarize in few slides, but roughly speaking, all those parameters, alpha, p, and n, they allow to tweak and adjust the functions, and they can help you to control the smoothness or the steepness of the functions. As I said before, those functions are binary functions. So as soon as we start stacking binary combinations, we start creating unbalanced N-ary construction. And to illustrate this behavior, let's start by defining a triangle simply as the intersection of three half spaces. And so far it looks okay. So I basically build a R function for three half planes. And then I'm going to increase the number of edges to my regular polygon. So now I move to 6. Once again, using the same R functions, we start seeing some kind of offset around this region here, where we would expect to have some kind of isotropic propagation of the vector field. We see that we have some kind of shift and offset. And of course, if I keep on increasing, so if I once again move to a nonagon, we see that the offset keeps on increasing. So my problem, and that's very important, is to somehow reduce this phenomenon. So, do there exist strategies to come up with balanced N-ary R-function? The answer is yes, and there exist several ways. The first one is to not to care and to transform the resulting unbalanced R function using some kind of iterative process that's called normalization, in which, roughly speaking, I don't want to enter into the details, we are going to use the gradient, the magnitude of the gradient, to adaptively scale the function. This approach is perfectly doable, and it has been used very successfully in mechanical engineering, for instance, but it is computationally expensive and might lead to numerical accuracies. The second one is simply to use the simplest R functions, the minimum and max functions, because those functions actually are well balanced and are straightforward to compute. However, their major disadvantage is that min and max function are local functions. What I mean by that is that the resulting R functions only correspond to one of the arguments of the functions. So the final result does not carry any additional information of all the other parameters. So there's no point to combine parameters if it's only to work on one parameter. So they are automatically discarded in my point of view. The second one that is really not elegant at all, brute force approach, should I say, to say, well, if the order of composition matters, then we are just going to compute all the possible combinations of the primitives. We are going to stack them all, and we are going to have something that's commutative. It is perfectly doable. It works. But it leads to a combinatorial growth of trees and combinations with, of course, computationally expensive and accuracy issues. There's this wonderful paper that Johan excavated a few months ago from Zenkins, and this methods that has been proposed once again in the early 70s, if I am correct, proposes a very interesting symmetric formula and differentiable mostly everywhere using only simple square roots. Its drawback is that it still requires a very large number of terms to be computed. Of course, Rachev himself proposed several strategies, and I mostly refer to what are known as chain functions that I'm going to present in a few slides. Biggest quality of this approach is that we now only need a linear number of terms to be evaluated, which is quite an achievement. But because there is no free lunch, we reduce the number of terms, but we lose some kind of smoothness near the zero set and the boundaries, where we might have a very, very strong variations. I'm going to illustrate that within a few slides. As a common point between all those functions, all those constructions, they come from functional analysis. Okay, nothing is geometric, and that's exactly my change of angle of approach for this presentation. I don't want to deal, as it has been done before, using functional analysis. I'm going to frame the problem using geometrical objects. So can we build geometric N-ary R functions? The answer is yes, and I'm going to show you how. Let's start with the simple case and the three-dimensional case for all those strategies to see how they can be used. So the first example to combine all the possible trees is expressed as follows. So we have three parameters. We know we are going to combine them in a pairwise manner. So we can compute all the way to combine them knowing that our functions are commutative, we can divide the number of combinations by 2. The second one, is it? Yes. Of course, advantage of this strategy, sorry, I forgot an information here. We can use any R function we want. So we have the flexibility to tune the resulting R functions the way we want. The second one, so as I mentioned before, the Jenkins formula. This one's interesting, very interesting. Once again, I simplified just for this slide to the case where we just play with 3-dimensional R functions. And what's really beautiful about that function is that eventually the first term just corresponds to the sum of the coordinates of the vector. The last term corresponds to the norm of the vector. And in between, we have a bunch of, actually all the norms of the projected vector onto subspaces. And by just alternating the signs here and there, we can build any R functions that we want. So it's a very elegant method, and it immediately answers to the title question. Can we build R functions using geometry? The answer is yes, because here we just use geometric concepts. We have a vector, we compute its norm, we project that vector onto subspaces, compute their norms, and just sum up the components. Beautiful solution. The chain functions of Hrvatchev, they might look complicated, but actually they are not. What matters the most in such functions lies mostly in those terms here, either the difference between components and its absolute value or the summations. For those who are familiar with neural networks and artificial intelligence, those are known as the ReLU functions or activation functions, because those functions, those terms, they identically nullify whether xi becomes positive or negative. Now, let's have a look at those functions to better appreciate how they evolve. I'm going to show you a demo in 3D. So we have here the first family of the first branch of our function using the maximum here. So on my example, I considered actually 3 spheres, and I evaluate the resulting R function of the union of those 3 spheres on the plane z equals 0. So we actually have 3 disks, and we are going to construct a assigned potential field for the union of those 3 disks. So here we see the maximum R functions. Here and there, we see that the strategy using brute force approach, combining all the possible R functions and Jenkins functions are not that very different eventually. And we see here the Hrvatchev chain function. For a better rendering, I'm going to show you up this. So we see we have 3 disks, okay? Each disk actually represents a distance to its center. So here we have the maximum function. Here we see the second type of function. So if I remember correctly, that's the brute force approach. Here that should be Jenkins functions, or this one, I don't know. And last one, look at Hrvatchev chain functions. We can see that as soon as we go away from the boundary, the function really strongly decreases, which is very problematic for people like me, because we want functions to be fit to models at real time. So if we have strong and very unstable variations, then it is extremely difficult for us to find a 0 set on real time. Up. Now, a quick and fair comparison between all those methods. So min-max functions, most efficient, simple, fast, and somehow adjustable using alpha-specific functions, not differentiable, but they are local functions, so totally useless for us. The symmetrized binary R functions, fully tunable, so we inherit all the desired properties of R functions, but it is computationally expensive. and the number of the growth of terms and trees to be computed grows combinatorially. Jenkins' construction is great. Once again, it is penalized by the number of terms that grows combinatorially as well, but this one's differentiable almost everywhere and is fairly direct to compute. And we have a last family of HF change functions that are linear in terms of number of coefficients to be evaluated. The differentiability is also tunable through the parameter m, but they really exhibit a steep and strong transition near the zero set, which is problematic in our case of immediate and fast reconstruction. Now, let's go now to my ID. My idea is to say, well, if our functions do not depend on the magnitude of their argument, why not expressing them in polar coordinates and setting the radius to be 1? And this is exactly what I have in the first equation. I took the RP functions, express it in polar coordinates, and we see that eventually our function of 2 parameters is only a cosine function plus or minus a threshold, plus or minus the control if it's the union or if it is the intersection. So eventually what it means that we can actually represent our function as a subset of some larger functions, which are this kind of trigonometric functions parameterized with this threshold. And here on the image on the bottom, I'm showing you what happens to the sign of the function when you actually tweak this plus or minus 1, which I call h parameter. So eventually, we do obtain our functions, so functions for which the sign is constant in each quadrant only for specific values, namely h is equal to -1 or +1. And in between, those are no longer our functions, but we can linearly interpolate in between the intersection and the union of objects, which is quite surprising. And at first sight, 7 years ago, because this is part of the last paper I wrote with YOHAN, I did not realize, but eventually this way of thinking as our function presents a very original way to do linear interpolations between Boolean predicates, which is quite surprising. I'm going to show you a demo to show you how this works. This is one of the good old R functions. Okay, I can choose the one I want. And eventually, by tweaking this H parameter, I can open or I can close my resulting function, okay? And to show you how the result is affected, I show you here, I have chosen 2 spheres this time, and eventually, by tuning this H parameter, here I represent the union, and then by moving it, I can linearly interpolate in between unions and intersection. Isn't that great? And quite surprising. And even more surprising, I can go beyond the union and I can go below intersection. Look at, I can go further than the intersection, which corresponds to this case when my object is totally closed. And I can go below intersection, let's say, for instance, this location here, where I can reduce my intersection. So that's quite surprising. And of course, the property holds and the logic holds for here I used R alpha, but I can use, of course, RP, RM, and the way I want, okay? And up, for instance, and to show you in 3D how this looks, back to 3D, so we can see how the function evolves. And we can see that actually my function, once again, exactly corresponds to a zero set and is positive for the intersection or the union as desired. So that's really, it took me a while to figure out and to frame this logic properly. Now, once we are there, we have mostly everything. So let's try to summarize our key observation from the 2D case. First, we have the magnitude independence, okay, which is the key to express the R function within the polar domain and setting the radius to be 1. We don't care about the magnitude, okay? Later, we can scale it back to make the function homogeneous, but we can compute the sign of the resulting function only using the direction and not the magnitude of the input parameters. The second observation is that when do we get R functions? Well, we get R function only for two and only two values, namely plus h and minus h, that corresponds to the intersection and the union, okay? And the same property holds for higher dimensions as well. And eventually, if we think about the impact of this h parameter, it simply controls how the domain, or the world, or the space is partitioned into two connected regions. So eventually, we have a coefficient like a cursor h that we can move to say, okay, I want my space to be fully closed, or I want it to open the way I want. So nothing forbids us to extend this concept from 2D to 3 dimensions on the sphere or 4 dimensions on the hypersphere and so on. So let's see what happens when we think about this extension to higher dimensions. I'm still on time? Yes, I'm still on time. Of course, our zero crossing half-lines becomes hyperplanes. The symmetry that I have not mentioned, but it is the axis of one vector. So this is this vector here. And eventually, we are no longer going to consider some kind of angle, as I mentioned in the parametric polar representation, but we are going to represent this as some kind of n-dimensional quantity. So if an angle was enough for a two-dimensional case, we could expect some kind of surface to be necessary for the three-dimensional case and so on. So the idea will be to somehow evaluate the part of the unit sphere that is intercepted with this opening. And the killing questions, the one I have partly answered, is that if we can compute the fraction of that surface volume or hypervolume, then we immediately get an R function. So let's frame things properly with less drawings and more math. So we are going to, on this case, to just represent the intersection case. So I just want to represent the space where all the components are positive and the union case is obtained by symmetry. So first we build a simplex whose apex is the origin. And we are going to interpolate each canonical vector with the pole with a parameterized spherical arcs. Each pair of parameterized vectors is going to define a plane or hyperplane that's going to open similarly to what happens when we do open an umbrella. And I'm going to illustrate that on the three-dimensional case. Before that, I think a drawing is much better. So we are in the 3D case. We have our pole here, which is basically collinear to the vector 1, 1, 1. And we actually create a bunch of vectors that we open similarly to an umbrella and that we can close. So eventually at the beginning, when h is 1, nothing's open, so we have basically nothing of the sphere that is covered. And the more we open, the larger the part of the sphere or the surface of the sphere that is covered, so which can be expressed as a solid angle until the end, okay? So the idea now is to say, okay, I now have this simplex. If for any given point in space, I can find the corresponding opening, then I just have to compare this opening to the one for which I know exactly when I have R functions. And by just doing the difference between these openings, this is an R function. Let's do things properly now. So we are in 3D for the sake of the example, and also because I'm still stuck with larger dimensions. So we have our pole, we have the unit canonical vectors, we have spherical parameterization to interpolate those arcs, those vectors from the pole. Of course, we choose the parameterization to be wise enough so that we interpolate both poles with convenient properties, as I have illustrated here. And from there, the question is, okay, what should we evaluate? As I mentioned, we need for any given point to find the corresponding opening of our simplex. And I have tried several strategies that work, all of them, before realizing something fairly simple. So first, I computed the area of a spherical cap, which which requires integrals and beta functions. And then eventually I observed that the ratio of some areas can be used to simplify the previous integrals, and beta functions can use volumes or hypervolumes for higher dimensions. This is still a remaining problem. But eventually I realized that I don't care, because what matters is that the quantity, whether it is a volume, an area, or a hypervolume, is a strictly monotone function of H, which means any opening uniquely defines a value, and the only thing I know is just to compute this H value and compare it to my R functions. And then the problem is over. So let's make a 3D case step-by-step example. So we have our spherical parameterization, the one I showed you on this example. So we have the canonical vectors, and we actually, that's this button. We actually have the pole here, okay, and we linearly, spherically parameterize this arc over the sphere that interpolates the canonical vectors. Once we are there, we can take pairs of vectors. So, of course, we can conveniently build an orthogonal basis using, okay, the sum of two vectors, the difference of two vectors, and the pole. And then, once we are there, we are going to express some coplanarity conditions. So, to make a long story short, the idea here is to say, okay, those planes that are drawn in yellow here, that keep on opening and closing, we are going to express some coplanarity condition of a point onto them. And eventually, good surprise, if you go through the simple mathematics, you eventually you finally obtain a closed form solution for this opening, which is quite surprising. And eventually, this equation simply states that, okay, in the 3D case, you just have to compute two determinants, okay, which basically corresponds to signed volumes, actually. And those A and C coefficients can just be used within some simple quadratic equation to find the corresponding opening. And once we are there, I was happy, but not that much, because eventually it's cool to get up with such solution. But since we have several pairs of vectors, and of course we might have opposite signs, I actually ended up with 6 solutions. So the sign can be fairly simply removed because we know we can easily determine which hemisphere contains the point by simply computing the dot product with the point with the pole. We know if it belongs to the upper sphere, the north sphere, or the lower hemisphere. Regarding the the three remaining values of our value maximum Hij, I could have used a maximum function because I want the minimal opening. So the minimal opening corresponds to the maximum height. But if I had done so, then I would have used a R function to build R functions. So that would have been stupid because I wouldn't have solved the problem. I would just have displaced it. But in 3D, it happens that each pair partitions clearly the sphere in three angular sectors, exactly like the center of an orange, for instance. So eventually, the adequate pair of indexes I and j can simply be determined by projecting the point P onto the equatorial plane. And yes, I'm still on time, yes. Consequence, there exists only a unique solution. And there we go. This is my solution. So here you have the function. So naturally, you see that the zero set exactly coincides as before. Here, this function illustrates here the result without making the function homogeneous. So it's just the sign of the function. It's not scaled by the magnitude. And the function on the right presents the scaled function that is homogeneous. So maybe I have it here in my demo. So we have those functions. So this is, you see, it exactly corresponds once again to the union of three spheres, scaled version and not scaled version. What's interesting about this function, and this one here, is that we graphically observe that the maximum intensity actually belongs to the area where all the three components, the three spheres interact. So it makes kind of sense. Before, we couldn't nearly see that. Here we clearly see, okay, we have three spheres, they generate some kind of potential field, distance field, and eventually the common area between the three of them is actually the one with the highest magnitude.
Johan, can I ask you to finish in 2 minutes?
Yes, I am done. So that's
Okay.
that's my conclusion. Of course, so far I am done with 3 dimensions. I'm working on extension with n dimensions. Still have problems to solve. With many applications in robotics, shape modeling, and AI with some new kind of neural network. So I really blew up the schedule, really. I am done with my presentation. Thank you very much for your attention. Do you have any questions?
Thank you very much, Johan. It was very interesting. As I said, I was very glad that you returned to your to academia and that your restaurant itself is going its own pace. Yeah, in the meantime, I just wanted to reach out to the Georgian group of logic. So in the meantime, when you were away, I worked with Revas on 3-valued logic. And I hope we can continue to work with Ramas and his team. So we're a little bit short on time. So if you want to ask questions or discussions, please email Johan. Now, I have a bit of ideas. I'm going to organize a few smaller sessions later after New Year with potential collaborations. So